This section 4.3 is about the trigonometric form of a complex number. So when we're talking about complex numbers, we're talking about part real and part imaginary. We typically will define these as, in standard form, as an a plus a bi. We'll talk about graphing complex numbers on a coordinate plane. And when we do that, we want to make sure we graph them correctly. The imaginary numbers will go on the y-axis, and the real numbers will go on the x-axis. So in other words, the bi portion will go on the y-axis, and the real portion will go on the x-axis. We're going to talk about the absolute value of a complex number, and all that the absolute value of a complex number is the distance that this number is from the origin. This definition up here will make sense once I show you with an example. So let me actually show you the example, and we'll go back to this in just a moment. So if I ask you to plot this point, this complex number, you would go over 5, and you would go up 3i. Again, this is just in the form a plus bi. So my a was 3, my a was 5, and my b was 3. So this is the coordinate point 5 plus 3i. If I asked you to find the absolute value now of this point, I'm asking you to find this distance that the point is away from the origin. If I draw a right triangle here, like so, we could find this distance just by using Pythagorean theorem. This distance would be 5, this horizontal distance, this vertical distance is 3, and so we would use Pythagorean theorem to find this side. We would say this side, if we want to call it, we'll call it r. We would say r squared would be equal to 5 squared plus 3 squared, and that would end up with 25 plus 9, which would be 34. And then to get r by itself, we would take the square root. And that's essentially what this formula up here is doing. You're taking the a value, which in ours was 5. You're taking the b value, which in ours was 3. You're squaring them, adding them together, and then taking the square root. So we're just using Pythagorean theorem to find this distance. Let's do it again. This time our number is just 5i. So that means I go over 0, the real number is 0, I go up to 5i. I can't draw a right triangle now here. If I want to find the absolute value, it's the distance from the origin. Well, that distance is 5, so my answer should be 5. Let me go back here, this was my answer for that previous one. Well, how would I get that using the formula? Well, if I write this in standard form, it would be 0 plus 5i. So the a portion is 0, the b portion is 5. Plug it into your formula up here, you would do the square root of 0 squared plus 5 squared. So you're doing the square root of 25, which is 5. When it's a vertical or a horizontal distance, you can just count it. When it's a diagonal distance like this one, you have to actually go through and use the a squared plus b squared, take the square root of that formula. Now we're used to plotting coordinate points as horizontal and vertical distances. For example, if I asked you to plot the point, I don't know, negative 5, 3, or in this case, negative 4, 3, you would go over to negative 4, you go up to 3. That is a regular coordinate point. But what we're going to be talking about now when we talk about trigonometric form is we don't necessarily want this horizontal and this vertical distance. We now want an angle and a distance of a ray. So I want to know what is the distance, or what is the angle that my point is away from my initial side. We'll call that theta. And I want to know what the length of this line is, and we call that r, the distance of the ray. So we've got some formulas that we're going to have to come up with to be able to find trigonometric form. So we've already talked about finding r in the previous example. If I wanted to know this distance, I would just use the formula square root of a squared plus b squared. If I want to know theta, to find theta, what I have to use is the idea of tangent. So the tangent formula would look like this. Take the tangent of theta to be equal to b over a. But I can actually solve this for theta by moving the tangent over. So really the form I want to use is the tangent inverse of b over a. This is the form you'll use. It's just derived from the tangent formula. How did I get that? Well, again, let's remember that this right triangle here, if this is going to be the reference angle, theta prime, which will help us to find theta, this distance here is b, this distance is a, so opposite of is b, adjacent is a. So that's why I could use the tangent formula to find theta. To find a, if I want to know this side, I can use, because it's the adjacent side, I can use the cosine. I know the cosine of theta should be equal to a over r, but if I want to actually just know what a is, I would need to get rid of the r. So I'd multiply both sides by r. And that would leave me with a being equal to cosine, let's write the r first. Let's write r times the cosine of theta. And to find b, I could find b by, let's see, b is the opposite side, so I'd use sine. So I'd say the sine of theta would be equal to the opposite over the adjacent. Again, if I want to just solve this for b, I get rid of the r. So we would say that b is equal to r times the sine of theta. So these are going to be four formulas that we're going to use. This is what r is equal to. Actually, we'll use this form of it. This is what theta is equal to. This is what b is equal to. And this is what a is equal to. Again, I should probably write this as r equals for this formula. We will use these four formulas to help us now write something in trigonometric form. And so that's what we'll introduce on the next problem. Okay, so trigonometric form of a complex number. I have it listed out for you right here. This is the trigonometric form. Trigonometric form is the r value times the cosine of theta plus I times the sine of theta. Don't worry about this z here. This is just, setting it up. We'll use the r times the cosine of theta plus I sine of theta. So let me write that formula down here. And if I think about this, it's nice to be able to list out what I would need to be able to plug into this formula. The things I need to fill in, I would need to know what r is, and I would need to know what theta is. Once I know this value, and then that value, I can rewrite my answer in trigonometric form. Right now, it's in standard form. Remember, standard form is a plus bi, comparing horizontal and vertical distances. Trigonometric form will compare a ray length, distance from the origin, and a theta. So let's first of all, let's plot this so we know which quadrant we're in. That's going to be a key portion, is that we have to know which quadrant theta is in, so we know what our angle really should be. So -5, we'd go over 5, and we'd go up 3. Our point would be in the second quadrant. So this would be the theta that I'm trying to find, and this would be the r length that I'm trying to find. So right away I know that the theta that I'm going to solve for has to be between 90 degrees and 180 degrees. Let's keep that in mind. Theta has to be between 90 and 180 when I come up with it over here. So remembering the formulas that we talked about, let's first find r. Well, I know the formula for r, which is right here, is the square root of a squared plus b squared. And in my problem, a is 5, b is 3. It's not the I, it's just the 3. So we'll do -5. I think I said a was 5, it's really -5. Plus 3 squared. So we get 25 plus 9. Square root of that is 34. So our r is equal to the square root of 34. Let's write that over here. Now let's find theta. Remember I said that the formula we should use for theta is this formula right here. Tangent inverse of b over a. So if I do that, if I find theta, I would do, let me write the formula down first. So theta would be equal to the tangent inverse of b, which is 3, over a, which is negative 5. Now, make sure your calculator is in degree mode. So tangent inverse of 3 divided by negative 5. I end up with negative 30.96. Negative 30.96 is not an angle that's between 90 and 180 degrees. So negative 30.96 is my reference angle. Really, 30.96 is my reference angle. That's this angle right here, because that's the reference angle in the second quadrant. I want to know the distance from here around. So to find that, what I would actually have to do to get theta would be take 180 and subtract 30.96. When I do that, I'm going to end up with 149.04. So I have the two things that I need. Again, it's really important that you make sure that the answer you get here is in the correct quadrant. And again, you're either going to get a first quadrant angle or a fourth quadrant angle. And this problem is a fourth quadrant angle, but you have to apply it to the second quadrant because that's the quadrant that our point was plotted in. So what's my final answer? My final answer would be if I plug these back into this. So let me do that up here. R, which is the square root of 34, times the cosine of, I'm not going to have enough room to do it right there, I just realized, so let me move it down here. R, one more time. R, which is the square root of 34, times the cosine of theta, which is 149.04, plus I times the sine of theta, 149.04. This would be my final answer in trigonometric form. For this next example, I'm actually going backwards from what we were just given. In the previous example, we were given a standard form, and we had to find trigonometric form. Now I'm given trigonometric form, r times the cosine of theta plus I times the sine of theta, and I want to find standard form. I want my final answer to be a plus bi. So the two things that I need to know what a is, and I need to know what b is. On the front page of our notes, we introduced some formulas for a and b. We said that a was equal to r times the cosine of theta, and that b is equal to r times the sine of theta. So in my problem, I know my r is equal to 3/2, and my theta is equal to 300. So let's plug that in. A would be equal to 3/2 times the cosine of 300. Now this happens to be on my unit circle. So using my unit circle, I would find that this is the cosine, which is the x value at 300 degrees is 1/2. And bring down the 3/2, that would be 3/4 as my a value. Finding the b value, I would say b is equal to 3/2 times the sine of 300 degrees. Again, the sine of 300 is on my unit circle. So going to my unit circle, I would find that it's negative square root of 3 over 2. If I use my calculator, I'm going to get the decimal equivalents, and I don't want that. I want to give exact answers whenever possible. So multiplying this out now, I'm going to get negative 3 square roots of 3 over 4. So negative 3 square roots of 3 over 4. So my answer in standard form would be 3/4 plus negative 3 square roots of 3 over 4, and then don't forget to put the I at the end. There actually is a much easier way of doing this than actually pulling out the formulas and multiplying in, or pulling out the formulas and substituting in. And that easier way is to just go ahead and use the distributive property, because that's essentially what we did. So when I multiply this out, I get the 3/4. When I multiply this out, I end up with the plus the negative 3 square roots of 3 over 4, and then put the I there. So again, you'd have to pull the values from the unit circle when you do the multiplication.